Hello, everybody. Good afternoon, everyone. Welcome back to the jetspace. We're excited to continue our guest lecture from last time with a second talk from our American topologist and differential geometer that's pursuing his PhD. I'll let him introduce himself. But yeah, just join me in welcoming him once again. We appreciate his ongoing contribution. Just stay engaged, bring good questions. The floor is yours, friend.
Awesome, thank you. So currently I am a PhD student, a fourth year PhD student studying stable homotopy theory and strong shape theory. So stable homotopy theory is like, how do you define homology theories and what are the relationships between homology theories? And strong shape theory is how do we extend homotopy theory to logical space that aren't like CW complexes or manifolds. And then I'm trying to bridge the gap and use stable homotopy theory to study strong shape theory and kind of create a strong stable homotopy theory. And uh, knot theory isn't my specialty, but I love knot theory, so I've studied it quite a bit, and I'm excited to continue. First of all, are there any questions? I knew that there were people who were interested in some of my questions.
Well, flexible though, if we do.
I'm guessing that's a no. So, if you have any questions,
You were
yeah, go ahead.
differential geometry or something along those lines, right?
Yes, I also do differential geometry and algebraic geometry. So right now, it's kind of between the intersection of differential geometry and algebraic geometry of Calabi-Yau manifolds. I'm working on Calabi-Yau manifolds. I don't want to go into the project into too much detail because it's not published yet. I am working on the algebraic geometry and differential geometry of Calabi-Yau manifolds. A lot from constructing them from the algebraic geometry perspective and analyzing them using tools from differential geometry and algebraic geometry.
Is it also connected to topology, or is that like a user connection?
Algebraic geometry and geometry for connection to topology. You use topology all the time in those fields. So they're my secondary specialties. So they're more of a geometry. They're less rigid, they're more rigid than topology. So you can't like bend things.
Right, like less degrees of freedom, I guess.
Yeah,
It
you can't.
relates to the work of that gentleman called Alexander Grothendieck or something, right? That French dude. He kind of
He was a French-German mathematician, Alexander Grothendieck. He studied algebraic geometry, set down the modern foundations for algebraic geometry.
And possibly category theory and even stuff like
Yep,
Hodge
category
conjecture, if I'm
theory,
not
tons of
mistaken.
other fields. Yep. Hey, any other questions?
That's really cool.
Yeah, thank you. Okay, well, I think we will begin it. So last time the video for the lecture last time cut off on the Jordan curve theorem. I want to finish and I want to kind of go over the Jordan curve theorem again really quick, and then we'll get into the algebraic topology of knots. So Jordan curve theorem. Okay, so this says that every embedded circle into R squared must bound an embedded circle, disk. Must bound an embedded disk in R squared. Okay, so now you might think this is obvious, but last time we showed there is a pathological embedding of the trefoil, like a trefoil-like knot, looking knot. And so the question is, how would you even say that it's diagram? It's projection. Diagrams are projections of knots. How could you say that that projection bounds a disk? And yeah, how can you say that it like pathological embeddings and bound disk? So we do have to show this because it's very important that we know that, and no matter what you do, you cut up the space only into a or an exterior component. Okay, so proof. Okay, we require inverse limits. So take a combinatorial knot. Take a combinatorial knot. Subset of R squared. We can parameterize K. We can parameterize K. K by a path gamma going from here. I'll rewrite that over here. In this, never mind. There we go. Okay, so gamma going from 0, 1 to 0, 1 to K and the base point of K, just a point in K. So 0 and 1 go from the same point, and gamma is surjective. Okay. So now, let's see. Oops. Okay, I have to go up here to do that. Sorry, this is a new whiteboard software that I'm using. Okay, so you have to click it with. There we go. Okay. So we started by defining a recursive set, recursive groups of set or class of sets of sets xi, which is equal to the first one is 0, 1/2, and 1. So we're taking the interval and we're taking the midpoint and the endpoints, or x1, sorry. x2 is just equal to the set 0, 1/4, 1/2, 3/4, 1. And then x3 is 0, this one's a little longer, 8, 1/4, 3/8, 1/2, 5/8, and 3/4, 7/8. Now, what are these recursive sets? Again, I'm taking the unit interval, cutting in half, taking these 3 points, and then in the next set, I'm taking these 5 points. Next set, I'm taking these 9 points. Keep on going. And so xi is just keeps on going. So I create these sets. What am I going to do with these sets? So we're going to take gamma, and define ki by having vertices being gamma of xi, and for a comma b in xi squared, such that a is less than, not less than or equal, but less than b, and b is minimal such element. So a being less than b and being a minimum such that a is less than b means that it's, for example, choosing this point, and then that means that b would be this point. So a would be this point and b would be this point. So for any such pair, take the straight line from, what is it, gamma of a to gamma of b. Okay. So what am I doing here? We're taking a combinatorial knot. So maybe we're taking a knot embedded in R2. And then what we're doing is we're taking points. Let's say we take xi, so let's say we have like 20 points. We take these points where gamma maps these points. Or let's say it just has this many points. And then we draw a straight line between each of these points. So it's going to it's going to be an approximation of our loop, of our knot. Any questions so far? Okay. So, and from here, sufficient large, or actually it's not even for sufficiently large. Let me get rid of that. Have for I in the natural numbers, ki plus 1 is isotopic to ki by an isotopy h of I plus 1. And then define, so then we can define going from I plus 1 to I to be h I plus 1 of x evaluated only at 1. Okay. So this gives our fi plus 1. And so now what we want to do is we want to show that there's an embedding of a disk. So what we're going to do is we're going to extend fi plus 1 I to the interior. So let's say we have this knot. We're going to extend and we map it fi plus 1 I, and it maps to some other knot, another approximation of a knot. It's another combinatorial approximation of a knot. Something like this. We're going to extend fi plus 1 to the interior of here, like to the interior of both of these knots. So, since phi 1 of r squared and a random point is 0, we can extend fi plus 1 let's say that every circle is centered around 0. So star in this case is 0, 0. This is equal to, okay. We can extend fi plus 1 I to fi plus 1 I tilde, going from the disk from the interior of ki plus 1 to the disk in the interior of ki. I'm doing loose with the interior. That's not what the interior actually means. Basically, it's the it's the bounded component of the bounded connected component of the complement of the loop of R squared. But that's really what and then the closure of that. That's really what these disks mean. So I guess we should note d squared I plus 1 is closure of bounded component of it'd be R squared minus ki. Okay. So we via null homotopies. Via linear, or piecewise linear, via PL null homotopy. So piecewise linear means that, or actually, no, we don't even need piecewise linear, sorry. Linear. Via linear null homotopy. Okay. So now what we really have is we can write a system of an inverse system. So taking C to be inverse of I in the natural numbers of these d squared I plus 1s to fi plus 1 I tilde. This is just going to be equal to, this set is going to be equal to the intersection of I in the natural numbers of the d squared I plus 1, or d squared I. Okay, so it's going to be, yeah, that's going to be the intersection of all these disks. We want this to be homeomorphic to, we show that? Well, inverse limits have the property that if you map into any of the approximations, the d squared i's, then you have, if you map into any of the approximations, and you can get such that, so if you have a map gi from squared I plus 1 to, or sorry, a disk. We have a map going from a disk to such that a collection of maps such that f of I minus 1 tilde of gi is equal to gi minus 1. Then we get a map into the inverse limit. Then, and there's the gone from d squared into C. Okay, so what we have is take the piecewise linear homeomorphism of G GI from say it's the interior of the 2 simplex 2d squared I plus 1. This is going to be a okay, let's see. What do we want here? Oh, I want to move here. Okay, so we want to show that it satisfies this property that I wrote above. Turns out it does. Of linearity, I'll let you check this on your own if you're interested, but by PL linearity, PL linear, piecewise linear means that some subdivision of the 2 simplex is take some subdivision of the 2 simplex, then the map onto d squared I plus 1 is going to be linear on that subdivision. So basically by linearity of the subdivision, we have, and the linearity of our maps, we have fi plus 1 I tilde composed of gi plus 1 is going to be gi. So inverse limits preserve homomorphisms. Preserve sequences of homeomorphisms, coherent sequences of homeomorphisms. So we have that delta squared is homeomorphic to C, which that means that delta squared is a disk. It's the filled-in triangle, and so we have that it bound that the curve bounded an embedded disk. Okay, so that's the Jordan curve theorem. Here's an exercise. I wrote this exercise last time. I can just scroll down like that. Okay, so exercise 6 or 5, sorry. Prove the crossing number, the unknot is the only knot with crossing number 0. Use Jordan curve theorem. Oops. Use the Jordan curve theorem on the projection, which we call a diagram. This is really a diagram. Okay. So now we can talk about the algebraic topology. Topology of knots. Okay, this is the more interesting part because this is going to deal a lot with manifolds. So we're going to look at specifically oriented manifolds. So we're going to define an operation on oriented manifolds and then see how those operations can be used to study the algebraic topology of knots. So this is gonna deal with some more algebraic topology and a little more advanced tools. So given two compact oriented manifolds. Oriented manifolds, M and N. Take two closed disks, dm in M and or I guess I should do dm and dn in N. And take or define an orientation preserving map phi going from dm. I don't know if I do bold or not. dn. Okay, so we take an orientation. So we have two manifolds. Let's say this is the two-hole donut. And then we take a disk on it, a closed disk. And let's say we look at the three-hole donut, and we take a disk here. We take an orientation preserving homeomorphism. Orientation preserving. I guess I should have said homeomorphism. I have to click with this. Case 7. Okay. This should be homeomorphism. Okay. We take a homeomorphism between these disks. And define the what's it called? I can't remember what it's called. Okay, just connected sum. There we go. I forgot. It's the connected sum. Define the connected sum of n, m and n to be m minus the interior in M of dm union n minus the interior in N of dn and union it along phi. Phi restricted to the boundary of dm. Okay. So what this is doing is we are taking these two manifolds and I'm choosing a disk, and then we're gluing along this, we're cutting the interior of the disk out, and then we're gluing the two manifolds along those disks. So it looks something like this. We're gluing these two manifolds together. Okay. So that's the connected sum. So here's an exercise. Prove exercise 6. Prove that any choices of disks dm dm prime in M and dn dn prime with a subset of n with phi going from dm to dn and phi prime going from dm prime to dn, that m minus the interior in m of dm union along phi of n minus the interior of n dn is homeomorphic to m minus the interior of m of the m prime. A lot of writing. Phi prime union n minus interior of n of the n prime. Okay. So prove that no matter what choice of disk we choose, what choices of disk we choose, we get a homeomorphic manifold. Okay. So now we're going to define Euler characteristic. Euler characteristic. So the Euler characteristic is given an n-dimensional manifold, and an n-dimensional manifold M, and phi of M to be the summation from I equals 1 to n of the alternating sum of the rank of Hn, the singular homology, or the cohomology of M with coefficients in 0. Okay, that's the Euler characteristic. So exercise. Exercise 7. Given two connected closed n manifolds, closed n manifolds.
Sorry, can I ask a quick question?
Yeah, go ahead.
In the Euler characteristic, shouldn't the sum start at I equals 0?
Yes, you're right. I equals 0. There you go.
Thanks.
Okay. Take two. If we take two connected closed n manifolds, M and N are closed oriented. I don't even think it needs to be oriented. I'm not sure. Maybe it needs to be oriented. But then Euler characteristic of M connected sum to N is going to be Euler characteristic of the Euler characteristic of N plus the Euler characteristic of Sn, or a minus Euler characteristic of S. Okay. So what are some properties that we can do with these Euler characteristic or connected sums? Well, construct cover spaces. So given a knot K subset of R cubed, we can construct the universal covering space of K tilde by K tilde is equal to the connected sum from I equals 0, I in the natural numbers of k. So if we just keep on connecting k's together, universal covering space. So an example, trefoil knot. Let's see if we can draw it this time. We just draw it like this and then erase some of the parts. So, oh, never mind that. Okay, just imagine this is a trefoil knot with the correct crossing. Then k tilde is going to look something like this, with looping around. And so on. With the correct loopings and everything. We can construct we can construct n covering spaces, not the universal covering spaces. Construct the n covering. Sorry, there we go. That's the distinction. Construct the n covering space. I equals 1. Very major distinction. Sorry about that. Okay. 7. We can construct I is equal to 1 to n. We can construct the n covering space by doing. Here's our trefoil knot. We can construct the n covering space by 1 connected side times. Yeah. Okay, so here's a definition. Given a compact oriented connected manifold manifold n without boundary, then the Euler characteristic of M is going to be written in the form of 2 minus 2g, where we define G to be the genus of M. Okay, so now we're moving on to the algebraic topology of knots again, or to knots again. Definition: given a knot K in R cubed, we define the genus G of K to be the smallest genus of compact oriented manifolds embedded in R3 whose boundary is isotopic to K. So we're taking all the surfaces. This is a cobordism problem now. If you're interested in cobordism, the question is, can we basically find a manifold whose not or whose boundary is a certain embedding of a manifold of another manifold. And so this question becomes interesting because we can define algebraic topologies on, or you can use algebraic topology on this manifold with boundary being K, and use our standard tools. And since a lot of our standard tools fail for the circle, like this, since knots are just circles, like we can't get a ton of topological information. If we extend the manifold so that its boundary is going to be not, then we can ask what are the topological properties of embedding. Okay. So then, last definition for a little bit. For a compact, for a knot K in R3, any compact connecting oriented, that's the wrong, it doesn't matter. Oriented manifold M, whose boundary is isotopic to K, is called a Seifert surface. A surface. Okay, so Seifert surfaces, these are going to be very integral to our theory of an invariant. For example, we're going to construct the Alexander polynomial using Seifert.
Sorry.
Yeah.
Sorry, could I ask a question about one of the earlier of the definition of the genus? Was this for a two-dimensional manifold or for a general manifold?
It's for general manifold.
But is the Euler characteristic always even, or do we allow the genus also to be a half integer?
Okay, so I guess this is going to be, let's just restrict ourselves to two-dimensional in this case because yeah, we're only embedding in R3. A characteristic for embeddings in four spheres, for example, you can have the Euler characteristics be like half integers and stuff. And yeah, so since we're in R3, let's just do two manifolds. And so yes, we're going to be G the genus. It's going to be even.
That makes sense. Thanks.
Yep. Okay, so now the question is, can we always construct a Seifert surface for a knot? Because if a Seifert surface doesn't exist, then these definitions aren't very useful. So there's a theorem called Seifert's algorithm. And it says every knot admits, every knot K admits a Seifert surface. A Seifert surface. Okay. So the proof, I'm just going to show Seifert's algorithm. I'm not going to be very rigorous about this one. So take a combinatorial knot K in R3 in general position with vertices in general position. Give K an orientation Give K an orientation. Okay, take the diagram phi of K. Resolve crossings. So what does that mean? So let's say we have a knot. I'm going to draw a complicated knot because this one's actually interesting. Let's see. Okay, this goes over here. Oh no, this crosses over. And then this goes under here. Okay, so let's take a complicated knot like this. We give it an orientation. And then, so we extend these arrows basically throughout the whole diagram. Okay, whenever there's a crossing, yes, okay, so whenever there's a crossing where the orientation forms the orientation of a circle. So what does that mean? So let's take this part here, where it goes here, goes here, goes here, goes. Let me change color. Let me change color. Okay, let's say it starts here, goes here, goes here, goes here. That is a circle. That is the crossings. What I'm going to do is I'm going to take all of these, and I'm going to take the diagram, and I'm just going to turn that into a disjoint circle. I'm going to draw that as a disjoint circle. And then let's say I have another color. This going around here is going to form a circle. And so I'm going to give that a circle, but that circle contains the other circle because the last one was contained inside of it. It was a subset of the other crossings. And then we're going to keep on doing this. And then we end up with a diagram, that was incorrect last time. It should have been this. Should have been this. So we start here, we go all the way around here. There we go. That forms the circle that contains this. So we then look at what is it? What's the next circle? We have a circle. We have a circle up here, right here. So we get a circle there, and you just keep on doing this. You keep on doing that until you get a set of disjoint circles. Diagram, maybe more circles, but you keep on doing that, and then what you do is take a disk. Let me turn back to black. Take a by the Jordan curves theorem. Curve theorem. We can take the disk, take a disk, bounding each, a disk bounding each resolved circle of phi of k. with orientation preserved. Preserved. Orientation preserved. Okay. So then the next thing is now that we've filled in, so we filled in all these disks, all of these with disks, all of these resolved circles with disks. Now you take those disks and you move them to the boundary of, take those disks, take disks, and glue their boundary along the path of K that projects to a circle that was resolved. So what does that mean? We're gonna take, let's go red again. We're gonna take this disk that corresponds to this path, or to this resolved circle, and we're gonna glue the boundary along the path of that, in the knot that lift. So like the knot is three-dimensional. This circle comes from a path in the knot, and we're gonna glue the disk along that boundary. And then you just keep on doing that. Keep on doing that for every single resolved circle, and this gives you a Seifert surface. This gives a Seifert surface. So this is just a quick sketch of the algorithm. If you want more detail, I'd be happy to talk about it later. This gives us a way to construct a Seifert surface. So every knot admits a Seifert surface. Okay, so now knot theory doesn't just deal with single embeddings of circles. We can also have links, for example. So definition: a link, combinatorial or smooth, the equivalence class of disjoint embedded circles in R cubed up to isotopy. So that means a link L is going to be the disjoint union of I equals 1 to n. So like n could be anything of S1 into R cubed, and then we're looking at that up to isotopy of the disjoint union. So, for example, there's the simplest link is this. This is just one loop around another. Okay, and we're gonna find invariance for these links, because invariance of these links can also give us invariance for knots. So, first of all, we're gonna find the linking number of a link L let's say, or the linking number, sorry, we define the linking number of two knots, k and k prime in or in R cubed to be denoted, which is denoted L of k prime to be the signed intersection number, transverse intersection number. Transverse, let me rewrite that. Intersection number of, oh, first of all, I should have a convention. Every knot emits a Seifert surface. We denote the Seifert surface as sigma of k. Okay. So be the signed intersection number of sigma of k and sigma of k prime. What we're doing is the Seifert surface of a disk, or of, so let's take these two links. Their Seifert surface. Their Seifert surface is going to be a disk. This one has a disk here. And then this one is going to be a disk here. And we look at the intersection number, the transverse intersection number of these two manifolds. Any questions with that so far? This gives a fun exercise. Exercise 8. A linking number of two knots is a link invariant. That and then you can so given two knots, whether it be a trefoil knot that are wrapped around each other, this linking number can change, and so that number is an invariant of give invariant on the link formed by these two knots. It's a fun exercise. Okay, now we're going to construct the Alexander polynomial from homology, and then I think we'll end it there, since this is going on for over an hour. So, really quick, theorem. Every sub-manifold of R cubed has a tubular neighborhood. So what this is basically, this theorem I'm not going to prove here, but saying any manifold, the circle, we can find a find a neighborhood in which on the manifold in which the neighborhood basically extends into R3. So an example of, like, let's say a sphere, we can find an open neighborhood, and then we can find a little extension of that neighborhood into R3, so that this is true for the whole manifold. So we're going to be using this theorem. So the Alexander polynomial the way we're going to construct it is take a naught k and its Seifert surface sigma of k. Then, since it's oriented and two-dimensional, h1 of sigma of k, the singular homology over the integers, is going to be isomorphic z plus 2g for the genus. G is the genus. We can choose. Oh, okay. I forgot. Since V is a Z module, or since, oops, since, let's see, since H1 is a Z module, and Z is a PID, principal ideal domain, then we can choose a basis, A1 of homology classes of A2G of homology classes. Of H1 of sigma K V. Okay, so we take its homology classes and we take its basis. Okay. Each cohomology class, so each cohomology, or each homology class AI has a representative AI in E1 of the first of the cycles, or of the not cycles, the what are they called? Coefficient group as a representative in chain groups. So the chain recall that H1 of the chain groups consist of the set of maps from alpha or A1 to delta 1 to sigma of x or k, and such that A1 or I is continuous. So, okay, let me write this better. A going from sigma k to, from the first simplex to sigma k. A is continuous. So we have representative AI going from, which is going to be a map from the first simplex to sigma k. However, since AI is in the kernel of the boundary map D1, then AI restricted to 0, 1 is equal to a point. This implies there exists by the universal property of quotients, there exists an AI prime going from S1 to sigma k, and that's what we're going to care about. Okay. Hey, so then the question is, we're going to take AI prime and aij as knots in, okay, and lift using tubular neighborhoods. Lift AI prime to a map, or I guess, let's see, AI prime tilde in, okay, so using a tubular neighborhood, lift AI prime to a map in the tubular neighborhood. Of sigma k. So what are we doing? Well, locally our Seifert surface is going to be a manifold. So we have our tubular neighborhood. And let's say we have AI. Well, then we're just going to lift AI off of our surface a little. And there we go. Into our tubular neighborhood. Then form a matrix. Then we're going to form a matrix. Let me get rid of that drawing real quick and move it over here. So yeah, we're taking our little tubular neighborhood and our knot, and we're lifting our knot into our tubular neighborhood. Okay. And so then define the Alexander matrix to be the linking number of AI tilde, or Aij is equal to the linking number of AI prime tilde with Aj prime. So this is going to give a matrix, and it's when we lift our stuff into the tubular neighborhood, we can only lift things so far because if you, for example, let's look at like the hyperbolic surface, something like this. If you take tubular neighborhoods here and tubular neighborhoods here, then you can only go so far in the tubular neighborhood because there's certain the neighborhoods start to intersect with each other. And so the tubular neighborhood basically says that you can find a neighborhood that these tubes don't intersect with each other. So we can only move the loops so high, but that causes some linking with some of the loops left on the surface. And so we're going to find the linking number between these lifted loops on the surface to be this Alexander polynomial. Then taking Aij minus T Aij, where T is just some variable, and then taking the determinant of that. Let me erase this really quick. taking determinant is going to be the Alexander polynomial of your loop. And so this gives us, using homology, we were able to construct a polynomial, and using module theory and homology, I leave it as an exercise to show that this is really an invariant of the knot. However, it shouldn't be that surprising since it's a homology. It's the homology of the Seifert surface. It's dealing with that. And so there are easier ways to determine the Alexander polynomial. Like there's an algorithm to calculate the Alexander polynomial. Veritasium actually has a very good video on how to calculate, like on knot theory, and just basically knot theory history. And I explain how to calculate the Alexander polynomial there. And right now, this calculation is an easy way to see that it is the Alexander polynomial is invariant of knot. And yeah, I guess we will leave it there since this is going on for an hour and 15 minutes, and I'm getting a little hungry, so I think we'll leave it there. Any questions?
I had two small questions.
Yeah. Mhm.
Well, seriously, thank you for the lecture. It was very nice, especially this last thing was very cool to learn about. I'd wondered to just very small things.
Yeah.
At some point, you mentioned that you used that the integers are principal ideal domain, but I didn't really see how this was used in this construction.
Since it's a principal ideal domain, you are allowed to. The rank is well defined. It's as a module.
Okay, but I guess because I thought we already had this isomorphism to the free group a priori, so we could already choose one. I guess, does it come into play in showing that it's well defined later? Or
yeah, no, the rank of a module depends on the ring that your module is over, and so since we're the free group over Z as a Z module, then yes, our rank is defined as
sure.
is defined as we would like it to be.
Yeah, okay. I guess, yeah, if it were another ring, you could choose a basis maybe of a different size, and then the invariant wouldn't be well defined or something like this.
Yeah, it would be harder to define it. So, for example, if you take B and as an R module, or an R module as, no, let's see. B as an R module and C as a C module, you get different ranks.
Yeah, sure. Okay, yeah, sure. I see what you mean. Yeah. And then thanks. And then the other thing, I think if you define the what are they called? Like the cycles or the chains. I always forget which is which. I think it should be the free abelian group generated by that set, no?
Yeah, the free abelian group generated. Yeah, so yeah, free abelian group. Yeah, you're right. Free abelian generated by over Z. Over Z. Yeah, you're right.
All right, thank you again. Thank you very much for the lecture. It was very nice.
Yeah, thank you. Any other questions?
Sort of a broader new question, if that's all right with you, Doc.
Sorry, what?
Whole topic, I guess, or a beginner question, if that's all right with you.
Yeah, that's totally fine.
These you mentioned, like homotopies, cohomologies, homologies, these are all different ways of tracking
I'm not sure what the word for it is, essentially holds in like these very high dimensional objects.
Mm-hmm.
Because you can't like visualize them easily. You basically track them using their dimensional invariance, for lack of a better word, right? So you
Yes.
can kind of tell the identity of something even when it's in a very complex high dimensional space by sort of tracking like the holes that it forms within a different, I don't know, schema or whatever you want to call it, like homologies or homotopy. Yeah, you get the idea, different things. Are these used in estimating like how certain mathematical objects will behave in higher dimensions, like functions and stuff? Is that the
Yeah, absolutely. There's something called obstruction theory, where if you take twisted homology, or not twisted, if you take homology groups with coefficients in being the fundamental group of your surface, you can show that certain functions cannot exist if they have certain homotypical properties using these homologies. So functions definitely have to behave certain ways on different surfaces. And there's something called oh yeah, go ahead.
So I mean, you used the term gluing, right? I
Yeah.
think that relates to the idea of like when you take something like a manifold, because it's like a kind of, I don't think it's like a computable thing exactly. It's almost like a weird continuous version of a graph almost. I'm not sure what exactly the right definition is, but you take something called a local slice of it called a chart or something, right? And then you operate on that. And the gluing thing you mentioned is when you try mapping those charts back onto the manifold. The voids you track allow you to predict whether they'll map back or glue back cleanly, right? So you can estimate how they behave.
Yes, exactly. And what you're describing is actually a homology theory called sheaf homology. So sheaves basically tell us the local behavior on you can use a sheaf to determine the local behavior on a manifold, and then glue that information back together to global structures. And then if you take homology of this sheaf, which I won't explain really how to do, but it tells you what obstructions there are to gluing via these holes.
So that's why we see this stuff a lot in topics like, again, unless I'm mistaken, a lot of this stuff pops up in physics, like, string theory, because they deal with like very high dimensional objects, right?
Yes.
Where this stuff generally comes in. Okay.
Yeah, well, string theory deals with, like, I think Jet would know a lot more on this. The topological properties of, like, brains that give different, like, configurations on, like, how the theory works.
I don't want to take up too much of your time, but is there a connection to ideas like space filling curves, if you're familiar with those, like Morton and Hilbert? Because I'm mainly just talking about it from like a software context. I'm basically a code monkey by trade. I run into things like Morton codes in things like textures visiting in GPUs, for example. Because when you have like a very like high dimensional thing, like even a 2D texture, computers sort of prefer that to be like very linear or flat. So you often achieve that by using either a Morton code or a Hilbert curve. Both of those are space filling curves, right? They can sort of reduce, they can fold dimensions almost. That's basically what they do. What I'm curious about is where do these sort of voids or these void trackers come in? Because what kind of problems are there where you can't just sort of fold the space using some kind of trick like that? Like different types of spaces, right? Like I'm guessing the space filling curves only apply to like simple spaces that up to a number of dimensions. I don't know if that's a complete nonsensical question.
There are higher dimensional analogs of space filling curves called space filling surfaces, where they fill an n+1 surface. So if you have an n, you can take the n plane and you can bend it in a way to fill the n+1 plane, stuff like that. But what you're describing is the relationship between these space-filling curves, for example, is called wild knot theory. It's not very well researched, because we don't really care as much about the wild knot. In my first lecture, I gave a construction, like the sketch of a construction of a wild embedding of a circle, and its projection is like a fractal, for example. You can have knots that project on the space-filling. I believe you could definitely have knots whose diagram are space-filling curves.
And is that where it kind of comes back to your specialty? Because you mentioned you do work where you bridge stable homotopy theory and something called strong shape theory, right?
Yeah.
Strong shape theory has some connection to things like fractal shapes or something where, like, it's essentially like some sort of tool for dealing with objects that are too nasty to deal with using stable homotopy theory alone or something along those lines.
Exactly. So strong homotopy or strong shape theory. Basically, we study spaces where homotopy theory is unable to differentiate these spaces, but they have different global structures. The strong homotopy, it does get into my research a little. So, for example, the Warsaw Circle has the weak homotopy type of a point, but it is not homotopy equivalent to a point. And so homotopy theory fails to account for the global structure of the Warsaw Circle. And so the way that strong shape theory is an extension of homotopy theory that allows us to differentiate that, yes, actually, the Warsaw Circle is not strong shape equivalent to a circle, and so there is a difference there. So strong shape theory agrees with homotopy theory on manifolds and CW complexes in every nice space, but once you get to locally complex spaces, like, for example, Hawaiian, which is just a circle, wedge with a circle, wedge with a circle, so on, all the way down. Once you get to spaces with infinite complexity at a point, then that's when homotopy theory fails, and strong shape theory and shape theory extend homotopy theory to work with.
Right. By the way, Doctor, do you have any kind of like, I think you may have posted elsewhere, like, do you have like any papers or any preprints or anything I could just look at? Like, if you have any links that you could post?
Yeah, I can DM you some links, but I'm not sure I want to put it in chat because I want to keep my name anonymous.
I get it. I'd really appreciate if you could DM those, like, if you're okay with that, if you're cool with that, like, I'll not mention like personal details or anything. I'm just curious.
Yeah. Sounds good.
Thanks.
Any other questions?
I mean, if no one has a question, I had a small question about the last lecture, if that's okay. I wasn't there. I watched it back on YouTube.
Yeah,
you mentioned we introduced these two notions of knots, right? Combinatorial and smooth, something like this. And I think you mentioned like that these categories are equivalent, right?
Yeah.
But when we talk about their categories, so you define these notions of isotopy between them, but these are all, so these categories are like groupoids, right? Yeah. Or is that what you mean by those categories, or is there like a, let's say, more general notion of morphism between not, where these are just the isos?
Well, the categories are equivalent in the sense that there's a functor from smooth knots to what's it called? To cognitive knots via the nerve. It's called the nerve functor. It's the nerve functor translates is an equivalence of categories in that.
But so it's really with, like, they're both groupoids. It's only those isotopies you're considering. No, nothing more.
Those isotopies, yep.
All right. Thank you.
Alrighty.
Any other questions?
I just have one little comment on something that I'm working on as well, which actually is kind of a strange, it might be its own program one day, some future mathematics, but there's something called signature theory, which corresponds to the way how random paths, Cadillac paths, move around. and they tend to get up, and paths themselves can get into weird knots in like three-dimensional space. There's something called a signature lift, which is very, very important for financial and data analysis stuff. So, and it, in and of itself, signature invariance are pretty related to knot invariance in a weird kind of spooky way. So I just wanted to throw that in there. But if there are no other questions, I think we're gonna have to let Mr. Age of Physics, by his Discord handle, go to lunch. So
Yeah.
I hope everybody had a great time. And yeah, I'll go ahead and end the recording. But it was a pleasure having such a great audience. So yeah.
Thank you for having me too.
All right, awesome.